What's up, ladies and gentlemen? Today we'll be talking about fluid mechanics and how objects flow through different types of fluids, whether it be air or water. Let's get it popping. So, what are fluids there? Fluids are specifically substances that cannot easily resist shear forces, okay? Meaning that they change shapes easily there, okay? Remember that shear forces are unaligned forces, okay? Um, Basically kind of going uh, crosswise against each other there, whereas compressive forces are forces that are coming together, okay? The type of fluids that we are concerned with are gases, such as air, and liquids, such as water. And up until this point here in all these different chapters and PowerPoints that we've been going through, we've typically ignored air as the effect of air is typically negligible in our considerations, though. Okay? However, in a lot of different activities, especially when implements are thrown there, water and air can certainly exert enough force to affect motion. And there are typically two different types of forces exerted by fluids on an object. Number one is buoyant force. Number two is dynamic force. And we'll take a look at those throughout this PowerPoint slide set. So, what is buoyant force? Buoyant force is the force that is implemented on an object due to its immersion in some sort of fluid, whether it be air or water. And with buoyant force, it always acts vertically, okay? Essentially trying to push that particular object up into the fluid, okay? And this is kind of the opposite direction of what an object's weight does. So an object weight typically pulls that object down. Buoyant force works in the exact opposite direction by pushing up. Okay? And a good example of this, if you try to push a ball straight down into a tub of water, you can feel a force pushing back on that ball as you try to push that ball into the water. And the force of that pushing up into the ball grows larger there as you push the ball deeper and deeper into the fluid there until it's fully submerged. So as I mentioned previously, buoyant forces do happen in air there, not just water. And we typically see this there when a balloon is floating in the air. And a lot of times for larger objects, like ourselves, for example, we don't think about air exerting a buoyant force on our particular selves there. And that's mainly because the difference in density between our bodies and the air is such, the gap in it is so great there. So while there is a buoyant force that's happening on us humans and other different objects there in the air there, that buoyant force is much less, okay, just due to air's density being much less there compared to our actual bodies. But it is there, and it's something that we do need to take into account in certain situations. So pressure, the amount of pressure there pushing down on you by either the air or the water is dependent entirely on the height of the column of air or water directly above you. Okay, it does not matter how much it is to your sides. So, for example, here you've got this square object here. Okay, there's a column, if you see by my cursor here. Okay, of air, and in this case, if this is in a tub of water, let's just say. Okay, there's a column there directly above this particular object, and it's pushed, as you can see by these blue arrows right here, it is pushing down on that particular object. However, what's important to note there is we don't just have pressure coming down on the particular object when it's in some sort of fluid. Okay? The pressure also comes from the sides, okay, as you can see by these arrows going left and right there, okay, and also pressure coming from the bottom. Okay, so there's pressure in any sort of fluid, whether it be air or water, on all different sides of a particular object. Now, so important to note there is the pressure increases linearly with depth. Okay, here's an example. If we look at a cubic meter of water, okay, cubic meter of water weighs approximately 9,800 newtons. So the pressure of water at a depth of 1 meter is 9,800 newtons. Okay, and that weight there will increase by an additional 9,800 newtons for every additional 1 meter depth of water. So if an object is 2 meters deep in water, okay, it exudes there real quickly 1,000 or real quickly there it'd be like 18,000 or 19,600 newtons of water or newtons of pressure there. Okay, if it's 2 meters deep into the water. Okay. What's also important to note is that the surrounding pressure increases by the same amount. So the pressure along the sides there, as you can see in this particular diagram, continues to increase as that object gets deeper, deeper, and deeper in that particular fluid. Now, how does pressure and buoyancy kind of come into play? Okay. Let's say, for example, okay, we got a meter, you have 1 cubic meter of water at a depth of 1 meter there, okay? And this cube, so this cube is a meter deep into the water there, okay? 1 meter deep there, and the particular object there is 1 meter cubed there. And what are the different forces that are happening on this particular object when it's 1 meter deep in this fluid? Okay? So first of all, we have 9,800 newtons of force pushing down on that particular object, okay? And it would be negative, okay, because the force is going down. The cube itself, okay, weighs 9,800 newtons there, okay? And it'd be negative, again, because when we think of weight, okay, which is, again, the force of gravity exerted on the mass of a particular object, okay? Now, the bottom of the cube is at a depth of 2 meters, so the buoyancy force, okay, the force that's pushing up on that particular object is going to be 19,600 newtons due to its pressure. So we've got, in our equation here, if we sum up all the forces going vertically there, we got 19,600 newtons of force pushing up, or buoyancy force. Then we've got negative 9,800 newtons of force pushing down, and negative 9,800 newtons of force there due to the particular mass and gravity of the particular object. Okay. So in this particular case here, the sum of all the forces would be 0, okay, meaning that this object will be floating at that depth of 1 meter. Now, what's important to note here is there will always be a greater pressure acting upwards on the particular object, okay, than downwards, okay? And the difference between the force pushing upwards compared to the force pushing downwards would not change, okay, regardless of the depth of the particular object there in that fluid. So how do we calculate buoyant force there? Okay? We could do it by this particular equation. Again, I'm not going to ask you to ask you to calculate buoyancy force there, but it might be good for those of you who are more mathematically inclined there to get a better understanding of the different aspects of what affects buoyancy force. Okay? So buoyancy force there is equivalent to the weight, okay, which in this particular equation is going to be P times G, where P is the density of the fluid and G is gravity's acceleration, okay? And then we take a look at the volume of the fluid, which is VF there, okay, that is being displaced by the object. Okay? And what I mean by being displaced by the object is if you push a particular object, okay, in a fluid there, the object being pushed down, okay, forces that fluid there to be pushed out to the sides, okay, and around that particular object. You might see this in a bathtub. If you sit down in a bathtub of water, the water level will actually rise. That's because your body itself there displaces some of that fluid there, okay? So that's what we're talking about here in VF there, the volume of the fluid being displaced by the particular object in that fluid. Okay. So buoyancy force there, okay, is also otherwise known as Archimedes' principle. Okay. And what's important to note about this particular equation is it's concerned with the density of the fluid, okay, and the volume of the fluid. Okay. However, it does not depend on the depth of the object in the particular fluid. So to understand what's important with buoyancy force there is we need to know how if a particular object will sink or float in a particular fluid. Okay, and this is dependent on specific gravity. So what is specific gravity? Okay, it is a ratio, essentially a fraction there, of the density of the object. Okay, um, or substance there. Okay, when it's compared to a reference standard. Usually, this reference standard there is water or air. Okay, so here's an example of that particular equation there. Okay, so P of O is the density of the object. Okay, and P of S is the density of the fluid that it's in, whether it be water, whether it be air. Okay, and with these water and air, there are specific reference standards which we'll talk about on a later slide. So what's important to note here is if the volumes of the object and the standard and the volume of the particular standard are the same, okay, then the specific gravity is equal to the ratio of the two masses. Okay, so essentially density, okay, is looking at mass divided by volume. Okay? So if we're trying to determine if something will float in a substance, okay, or sink in a particular substance, okay, if we take a look at this fraction here, okay, if the fraction ends up equaling a specific value that is less than or equal to 1.0, okay, that particular object is going to float. Whereas an object with a specific gravity, okay, that is greater than 1.0 will sink. Okay? If we would want to keep this in more simple terms there, okay, if the density of the object is greater than the density of the fluid it's in, okay, that object will sink, which makes sense. A more dense object compared to the fluid it's in will sink, versus an object, okay, that is less dense than its surrounding fluid will float. So here are some specific densities that we look at with reference standards there. Okay, so we know that water is approximately 1,000 kilograms divided by cubic meters. Looking at air there, okay, air is approximately 1.2 kilograms, okay, per cubic meter there. So those are two different fluid reference standards. Humans, depending on how much of their body mass is made up of lean tissue, okay, versus fatty tissue, their density can fluctuate there. Okay? And a good rough estimate of that is going to be 990 to 1,090 kilograms divided by cubic meters. The reason why this fluctuates so much there is that human bodies are made up of fatty tissue. Okay? Fatty tissue is approximately 900 kilograms divided by meters cubed in density, versus non-fatty or lean tissue, things like bone, things like skin, things like organs, things like muscle, okay? That's going to have a density of approximately 1,100 kilograms divided by cubic meters. So if you compare the typical human there, okay, in air, okay, notice how humans are a lot more dense than the air is. So it makes sense that human beings there are going to sink in air. Now, what's important to note there, if we compare humans to water there, okay, some humans would sink in the water, okay, others may float, okay, depending on how much fatty tissue they have, okay. So someone with more fat, okay, compared to lean tissue there, okay, their density might end up causing that particular human's body there to be less dense than water, okay, meaning someone with more fat on their body has a greater chance of actually floating in the water, okay, compared to somebody who has less fat and more lean muscle tissue. Now, if we take a look at the human body there, floating there, okay, if you were to try to lay flat in the water there, okay, with your legs straight there, okay, it's very difficult to float in this particular situation there, okay. So what you might notice here is there's a torque that's happening at your body in this particular situation. Okay, if you've ever laid in backwards in the water like this, okay, you might notice that your body wants to turn, okay, with your head coming up and your legs going down. Okay, and that it's important to know why this happens is because weight and buoyant force are not aligned. Okay, they are eccentric forces. We know that weight acts through the center of gravity of the particular individual there. Okay, so if you look at this top picture here, okay, you got the center of gravity here, okay, and you see that W there, okay, the force W there is pulling that object down, your human body there. However, buoyant force acts through the center of density, okay, not the center of gravity, the center of density, okay, which in general is typically closer towards a person's head. Okay? You'll see it by this dot right here. So this dot right here is going to be your center of density. And the buoyancy force pushes up against this, okay? And notice here now this is an eccentric force. Okay, here's the center of gravity, but the force is happening outside that center of gravity, causing a turning force. Okay? And the reason why that floating typically works better if you allow your knees to bend, okay? Because when those legs there, okay, bend, it moves the center of gravity in this case to the right, okay, closer to the head, lining up the buoyancy force, okay, and the force of gravity there. Okay? And when those are lined up there, that allows you to float. Moving on to another topic there, okay? Let's talk about dynamic fluid force, okay? When you see that word dynamic, think of moving, okay? And what dynamic fluid force is the force, okay, due to an object's movement or motion there in a particular fluid, okay? Whereas buoyant force acts vertically, okay, and is always present in a fluid, dynamic force will only be present there if the object is actually moving within a fluid. Okay. Now, what's important to note here is dynamic force is proportional to the density of the fluid, okay, which is letter P down here, the surface area of the particular object, which is the big letter A, okay, and the relative velocity of the object in the fluid, okay, which would be V squared here in this case. Okay. All those things multiplied together will give you the dynamic fluid force. Now, I keep using this term relative velocity, okay? And why do I use that term relative velocity, okay? Number one there, relative velocity is going to be the biggest impactful contributor to that dynamic force, okay? So whereas if we look here, look at the surface area of the object, okay, and the density of fluid all play a role in dynamic force. Because velocity is squared, that means the velocity of the particular object, relative velocity there, okay, is going to have the biggest impact there, okay, on this dynamic force in changing it. Okay. And what relative velocity is specifically is the difference between the object's velocity and the fluid's velocity. Okay. And let me just give you a quick example of this. Okay. Let's say you throw a football, okay, and when you throw that football into a headwind, meaning that there's air coming at you, and you throw that ball into that headwind, okay? What relative velocity is saying is it takes the velocity of the football, okay, going through the air, and it takes the velocity of the wind coming at you, okay? And knowing those two values there, we can calculate what your relative velocity is going to be, okay? So you have to take all that to account, the speed at which the air is coming at you and the speed at which you throw that particular object, okay, into the wind, okay, or maybe let's say you had the wind, instead of coming at you, maybe it was coming from behind. You would take the velocity of the football, okay, and you would take the velocity of the wind coming from behind you, and you would use that there to calculate what your relative velocity is going to be. And here's a visual representation of dynamic fluid forces there, okay, as things like the surface area, fluid density, and relative velocity. And what you'll notice here, For dynamic fluid forces there, as an object gets faster and faster and faster, okay, going to the right here, the relative velocity's effect on dynamic fluid force will be a lot greater compared to the fluid density and to the surface area of the particular object. So up here, okay, this top diagram there, okay, this takes a look at dynamic fluid force there, okay, and with this particular diagram, okay, we've got two different fluid vectors there, okay. So we got the weight of the particular object, okay, and we got the object's path there, okay. And then from that there we get a resultant dynamic fluid force due to that, okay. And the two, with dynamic fluid forces there, okay, there are two main forces there that affect, okay, dynamic fluid force there, okay. We've got drag force and we've got lift force, okay. Drag force and lift force, and they are highlighted here, okay, by this blue arrow down here and this blue arrow pointing up here, okay. We'll talk about drag force and lift force in the coming slides. Okay. So what is drag force, okay? Well, drag force is the part of dynamic fluid force, okay, that goes in the opposite direction, okay, of the relative motion of the object in the particular fluid. And a good example of this is going to be air resistance, okay? So as I throw this, let's say frisbee here, to the left, okay, there's a fluid drag force, okay, opposing that motion, okay, going to the right. It's important to note here, drag force will always decrease relative velocity if it's the only force acting on the particular object, okay? So again, drag force there is going in the opposite direction of what the particular object is traveling there in the fluid. If you wanted to calculate drag force, here would be the funky equation there, okay? A few different components of it, okay? Coefficient of drag there, which is CD, okay? Fluid density, which is P, okay? The object's cross-sectional area, okay, which is perpendicular to the relative velocity, okay? And V is, again, is going to be the velocity of the object with respect to that fluid. Okay? Again, if you look at all these different variables there, okay, since velocity is squared, okay, velocity, the change in velocity is going to have the greatest impact on drag force. Okay. Now, real quickly here, okay, let's review power. Okay, so power is the rate at which we do work. Okay, so essentially, okay, W, amount of work, divided by change in time there. Okay, and remember, what we can think about work being is the amount of energy, okay, an object either gains or loses. Okay, so we can think of power as thought of as the rate at which something uses energy. Okay, and we could change this particular equation there, okay, by understanding that power can be considered the average force multiplied by the average velocity, okay? So power is average force multiplied by the average velocity. If we take that particular equation, okay, power is force times velocity, okay, and in place of force there, okay, we can plug in our drag force equation, okay? What you'll notice here in our new power equation, okay, it looks very similar to what we had up top here for the dynamic fluid force there, okay? But velocity is cubed in this particular case, okay? So what this means here, okay, is that if we multiply our velocity by 2, okay, meaning we speed something up twice as fast as what it normally does, okay, this requires 8 times the power, okay? You might have experienced this, okay, if you're kind of just moving your arm in a pool. Let's just say you're standing in a pool and you're moving your arm in the pool. If you move your arm slowly, okay, it is pretty easy to move your arm in the water. Okay. However, if you try to move your arm very quickly in the water, you'll notice that the force resisting against your movement increases dramatically. Okay, and this is why. Okay, because as velocity increases, okay, it requires a ton more power to be able to to allow you to be able to move faster in the fluid. Okay, so because a lot more power is used to speed up a particular object in a fluid, okay, this requires a lot more energy. Okay, and this is one reason and why, okay, drafting is such a big deal in a lot of different sports. Okay, so here's an example of a race there. Okay, all four of these cyclists are on a team. Okay, and what you'll notice there is they are drafting. Okay, meaning the person in front there, okay, is going through the fluid first. Okay, and the people behind the first cyclist there, okay, are drafting behind. Okay, so because of this effect here, okay, of drafting, okay, this person in front there, okay, is going through the fluid first. Okay, they have to expend a ton more, going back to our equation down here, okay, they have to expend a ton more energy to create the power necessary to fly through the air, versus these people in back don't need to work nearly as hard, so they can conserve energy for later in the race. Now, depending on the study you're looking at there, how much drafting may benefit athletes here, okay, but it's been shown to reduce drag, okay, by 27 to 50% there in cycling. Okay, so if you were looking at a cyclist traveling in 20 to 30 miles per hour speed there, okay, wind resistance is going to account for 80 to 95% of the total resistance they are experiencing. Okay, so if we can cut this up to, or cut the amount of resistance that these cyclists are experiencing there by up to 50%, okay, that means these riders that are drafting off of the lead rider are going to save a ton of energy. Now, one thing to note here is there is a small benefit to the lead rider as well. Okay, they essentially get a push from a reduction in trailing turbulent air. Okay, we'll talk about this a little bit later on in the PowerPoint slide set, but just understand there is a little benefit for the lead rider out front here. Okay, but the amount of extra push they get is going to be much less than the drag that's being cut off there by the people in the back. Okay, and so this particular reduction in drag force is going to be roughly 2% for the lead rider. So in this particular case here, the lead rider is actually experiencing a 2% reduction in drag, but 2% is much less than 27 to 50% by these rear riders. And we'll talk about this little push there from the trailing turbulent air a little bit later on in this PowerPoint set. So one of the effects there on drag force there is going to be the coefficient of drag. Now, coefficient of drag essentially is just some number, okay? And this number there is affected by several different factors. Number one is the roughness of a surface, okay? So typically, the rougher the surface of a particular object, the more friction forces are going to occur of the particular object as it travels through the fluid, okay? Therefore making it more difficult to move. Good example, this might be sandpaper. Sandpaper is rough, okay? It does not glide across a surface as easily because it is rougher. Number two, viscosity of the fluid, okay? So slower flowing fluids are going to be more viscous than faster flowing fluids, okay? Meaning fluids that can move very quickly, okay, are going to be less viscous than fluids that move very slowly. An example of this might be comparing water to syrup. Syrup is a lot slower moving, therefore syrup is going to have greater viscosity, okay, compared to water. So if you were to swim in a vat of syrup there, you would have to expend a lot more energy to move through syrup than you would have to through water, okay? Because that, again, a more viscous fluid creates more friction between the fluid molecules and the object. And number three there, the shape of the object, okay, can affect the coefficient of drag. A more streamlined shaped object decreases that coefficient of drag. A good example of this might be comparing a football to a soccer ball. So a football is pointier in shape, therefore it's able to cut through the air, okay, more easily than a soccer ball. Therefore, a football would have a smaller coefficient of drag compared to a soccer ball. So with our drag force, okay, the size of the drag force is proportional there to the acceleration, okay, in this particular case, the slowing down acceleration of the fluid molecules as they pass the object, and to the mass of the objects that are slowed down, okay, meaning that the greater the decrease in velocity and the faster the rate of decrease, the greater the drag force. So again, as I've been talking about before there, more velocity, okay, and means that there's going to be a greater amount of drag force of that object in a fluid. And drag force there is produced in two different ways. We've got surface drag and form drag. Surface drag, okay, also is otherwise known as skin friction or viscous drag, okay, kind of similar to what we talked about previously, okay. Now, what surface drag is, as fluid molecules flow over the surface of the object, okay, the friction between the surface of the object and those fluid molecules flowing over the object, okay, this friction there slows down those fluid molecules, okay. Now, these fluid molecules that are directly against the surface of the object, okay, these molecules would slow down the next layer of fluid molecules, and next layer of fluid molecules, and next fluid layer of molecules, and so on and so forth. Okay, so what surface drag, therefore, okay, is proportional to the total mass of the molecules slowed down, okay, and the average rate of change of that velocity. Okay, and surface drag is affected by these several different factors: the cross-sectional area of the object, density of the fluid, relative velocity of that object, okay, the roughness of the surface, and the viscosity of the fluid. Again, things that we have talked about previously. Now, how do we, in a lot of sports here, we might want to reduce surface drag. Okay? Reducing surface drag there will allow us to move faster in that particular fluid. Here's a couple examples. On the left here is a speed skater. Notice the speed skater is wearing a smooth, skin-tight suit. Okay? And what this does there is makes the surface around this particular speed skater more smooth, okay? Meaning as this speed skater there, okay, skates and flies through the air, okay, the air molecules will more easily flow past this particular speed skater, creating less surface drag, meaning that speed skaters are able to reach a faster speed and maintain that faster speed without expending as much energy because surface drag is decreased. Here's another example here, okay? A swimmer. Now this particular swimmer here has a skin-tight suit. You also notice that this swimmer there, okay, the hair on his body, okay, is virtually gone. He will oftentimes shave his body, and that again reduces surface drag. Thirdly, while he does have hair on his head, okay, he wears a swim cap when he's in the water, kind of similar to what's looking over here on the left with the speed skater. This also will reduce surface drag, meaning that he can swim through the water faster. Yeah. Now, along with surface drag, we've got form drag there. Okay, form drag could also be known as shape drag, profile drag, or pressure drag. Okay, well, we need to understand there with form drag is that as fluid molecules strike the object, okay, they bounce off of that other object, okay? So if a soccer ball is flying through the air, okay, there are air molecules, okay, coming, or that the soccer ball is going to hit as it goes through the air, and they bounce off the soccer ball. Now, what's important to note there is as these fluid molecules hit the soccer ball and bounces off, those air molecules will hit the other air molecules closer to it, okay? And these will send the air molecules back towards the object. Bounces off the object, okay? Goes back, hits other air molecules. Object, air molecules, object, air molecules. Just bouncing back and forth, back and forth, back and forth, back and forth. Okay? And these molecules in the fluid there wind up following the shape of the object. The object there is exerting a force on those molecules to change their direction, okay? And because those air molecules will ricochet off other air molecules and come back to the particular ball or other object there, okay, those molecules are going to exert a force on the particular object. the larger the changes of direction, okay, the larger the forces that are being created there with form drag. Now, what you'll notice here is not only will these air molecules, okay, ricochet off the front of the object, okay, but they'll also ricochet, okay, over the top, bottom, left, and right side of the objects. And then even at the rear of the object, okay, as those air molecules flow past there, they will actually ricochet off the rear of the object, okay, hit some air molecules, and bounce back, hitting the rear of the object again. Okay. So therefore, okay, there are some air molecules, okay, bouncing off the rear of the object. And those bounces off the rear are kind of like small little pushes on the particular object there, okay, towards the air. Okay. So essentially, the air molecules bouncing off the rear of the object will help speed up the object through the air just by a little bit. Okay. Now, the important thing to note here is that those air molecules bouncing off the rear of the object, okay, they are only present there if the fluid molecules stay close to the particular object. Okay. And I'll show an example of this in one of the coming slides on situations where this would be the case or this wouldn't be the case. So with form drag there, okay, there are some air molecules bouncing off the front, and there are some bouncing off the rear. The ones bouncing off the front are resisting movement. The ones bouncing off the rear are assisting or helping with movement. And the difference between the forward and backward directed forces there is going to be that form drag. So with form drag, we need to understand how these air molecules flow around the particular object. Okay, and one of these important concepts there is going to be laminar flow. Okay, and what laminar flow states is that when the molecules remain close to the surface of the object. So you'll see this particular, let's say it's a football, it's being thrown to our left as we're looking at this, meaning the air molecules are flowing around this particular object from the left side to the right side. Okay. So you'll notice here these air molecules flow very close to the particular object, okay, from the front all the way to the back. Okay. Now, what's important to note here is if the change in surface curvature is going to be too large, okay, meaning this abruptly changes, okay, or if the relative velocity of the particular object is too fast, meaning the object is moving too quickly through the fluid, the molecules, instead of being very close here, will separate from the surface in the back. And again, a coming slide will show a better example of this. Okay, so the kind of the opposite there of laminar flow is going to be turbulent flow. And turbulent flow occurs when the fluid molecules separate away from the object. Okay? So what you'll notice here in this particular object, okay, it was immediately cut off there. And so instead of the fluid molecules flowing nicely around this particular object, okay, gets to the part where it's cut off, and these fluid molecules have nothing to flow around. So when this happens, okay, they become very disoriented, discombobulated, okay, very chaotic. And what this does there is it creates a lot of commotion there in the back, okay? And what this means there is these air molecules are not able to assist with the forward movement at all because there's no object for them to bounce off of, okay? What this does is increases form drag. Let me kind of explain what I just mentioned there, okay, up front here. Now I want you to look at my cursor here, okay? So with my cursor, with these air molecules in the front, okay, as they collide with the object in the front, okay, they'll ricochet off the front of the object, bounce up and hit another air molecule. Bounce forward, okay, bounce, hit, bounce, hit, bounce, hit. So these are what I was talking about previously, where the air molecules are resisting movement in the front. Okay. However, as these air molecules go around the object, okay, they'll hit the object, hit some more air molecules, hit the object, hit more air molecules. And the ones in the back here, okay, will hit the object, okay, hit some air molecules, and then hit the objects here, okay? So notice these forces are coming from the rear of the object, and since they are ricocheting to the object this way, they are helping assist with this object going from right to left, So let me repeat this there. There are small pushes happening with the collisions of the air molecules in the back, assisting with some forward movement of this particular fluid, or particular football in this fluid. Now let's compare it to this particular object. So in this particular object, yes, there are air molecules bouncing off the object and hitting other air molecules, slowing down its movement. Now as we go around the object, we would expect these air molecules in the back to ricochet and hit the object, propelling it forward, but the object's no longer there. Okay, it's been cut off. So these air molecules are not able to push as much. There's a lot fewer ricochets in the back compared to the front. So therefore, this slows down the object. So this is why, okay, we want laminar flow to allow this object to travel smoother through the fluid, okay, travel faster. This object won't travel as fast through the fluid. So form drag there is affected by the cross-sectional area of the object, density of the fluid, relative velocity, surface texture, and the shape of the object. Okay. And specifically with the shape of the object, if we want to reduce form drag, okay, an object should have a streamlined shape. And a streamlined shape there is going to be long in the direction of the flow of the fluid with a gentle curvature. Not an abrupt curvature like this object shows right here. This would be an abrupt curvature. We want a gentle curvature. So notice this is gentle in the back. So here's some examples of how we might streamline, okay, to reduce form drag in particular sports. Okay. Instead of being a bike rider here, okay, this bike rider is hunched down, creating a more streamlined shape, with more laminar flow off the back, allowing this bike rider to ride faster because form drag is reduced. Let's take a look at these two skiers, standing straight up versus crouched over. The crouched over rider there, okay, is a more streamlined, reducing form drag. And not only that, by pushing his or her ski poles out the back there, this creates a more gradual, streamlined shape, okay, allowing for these air molecules in the back to bump the skier in the back, helping propel him or her forward more, faster. And let's take a look at these two boats, okay? So this boat down here has a more gradual change, okay, in its shape versus this boat right here is more rigid and it's not as gradual of a change. Not only that, this boat here has a larger form drag because the boat is a lot higher out of the water versus this one's very close to the water. So this boat down here will have less form drag compared to this boat up top. Let's take a look at some golf clubs heads there, okay? We've got an iron and a driver, okay? So both want to hit the ball to the right, but the driver there, notice how it gradually tapers off the back. And this gradual taper off the back allows this this golf head there, or this driver here, this golf club, okay, to swing faster through the air because it's more streamlined shape in the back, allowing those air molecules to bounce off other air molecules and bounce into the golf club head, helping assist it with forward motion. So how do we reduce drag force there? Okay. Number one is go to higher altitudes. Okay. So because in higher altitudes, higher above sea level there, okay, such as higher up in the mountains, there's less air density up there. So fewer air molecules, okay, in the air. And so because of that, air density decreases, means objects can travel through the air there much more easily. Okay. Also, though, warmer air and more humid air, okay, will also decrease air density as well. Okay, so warmer air, more humid air, and higher altitudes will all reduce drag force. Another thing we can do to reduce drag force, we can streamline equipment and clothing. Okay, so those examples I showed previously with the golf club head, with the biker, with the rower, okay, with the speed skater wearing the skin-tight suit, and with the swimmer there wearing the skin-tight suit and shaving his body. Okay, all those will reduce drag force. Smaller surface area, okay, at slower speed. So smaller surface area And if you move slower, those will also reduce drag force. Smoother clothing material, as I mentioned. Okay. When possible, it's better to travel in the direction of the fluid flow, okay, when possible there. So for example, if I was swimming in a river, it would be easier for me to swim with the direction of the flow of water, where the water is kind of pushing me from behind, versus trying to swim upstream, okay, against the flow of the water. Likewise, if I'm running, it's easier for me to run with the wind at my back compared to running into the wind. Also, we can reduce drag force by drafting off of another competitor. Now, in some cases there, we might actually want to increase drag force. Okay? For example, a parachute. Parachute, we want a ton of drag force to slow us down as we're falling from the sky. Okay? Here are a couple examples though. Paddles and oars, okay, increase drag force in order to help propel a boat forward. So as you put those oars into the water, we want the flat side of the oars, okay, to be facing the way that we pull. Okay? And we do this there again because that will help pull more water. In this case, we want to increase the drag force of the oars through the water because that gives us more force to help propel the boat faster through the water. If you're maybe running in a pool for training or rehab, we want more drag force there, okay? Because with more drag there, from training purposes, helps us to push harder, or maybe rehab purposes, because I want to limit how fast I can move, okay? Both of those would be examples of where we would want to increase drag force. Or in some other case there, if we want to push against a greater resistance there, in order to exhibit some sort of training effect, okay? Increasing drag force might be beneficial. For example, some people will run with a parachute at their back because running with a parachute at their back makes it more difficult to run forward, okay? Therefore, increasing muscular strength, okay? And might be used to help provide some resistance to assist with some sprint training. Now, the second component of dynamic fluid force is going to be lift force. We've been talking about drag force this entire time. Let's talk about lift force, okay? Here's what's important. Make sure you star this or something along those lines. Lift force acts perpendicular to the relative motion of the object in the fluid, okay? So in this particular case here, okay, lift force here, okay, would be this upward arrow in this particular diagram. Okay? Now, unlike with drag force, which goes in the opposite direction of the relative motion, okay, lift force changes the direction of the relative motion of the object through the fluid. Okay? Example here, if this object was being thrown or was moving to the left here, the lift force will help also propel this object up. Okay? Now, as the fluid changes direction, okay, as it moves through an object, there's an opposite acting force is applied back to the particular object. Okay? Lift force is proportional to the mass and the lateral acceleration of the particular fluid objects or fluid molecules. Here is the equation for lift force. Note it looks very similar to the equation for drag force. Okay? CL, though, is the coefficient of lift. P is fluid density. A is the cross-sectional area. Okay? And V is going to be velocity. Okay? Now, again, similar equation there to drag force. Okay? The only difference is going to be this coefficient of lift variable there. Okay? Versus in the other equation, we had coefficient of drag. Just like with with drag force there, velocity is going to play the greatest impact there on lift force. What's also important, though, is the orientation of that surface area. Okay, and we'll talk about that a little bit later on in some of the slides there. Okay. Now, what's important to note is while lift force, the name of it, lift, we always think of coming up there. Okay, lift force can also act down as well. Lift force could also act left. Lift force could also act right. Okay, so lift force can happen in any direction, not just up. Okay. So in order to understand lift force there, we need to understand Bernoulli's principle. Okay, what Bernoulli's principle says is that faster moving fluids will exert less pressure, okay, laterally than slower moving fluids. Essentially, faster fluid, okay, less pressure. Slower fluid, more pressure. If fluid molecules are made to move faster over the top of an object, pressure will be reduced from above, allowing for greater lift in an upwards direction. Okay? So if a particular object is flowing in the air and the fluid molecules along the top of the objects are moving faster, okay, what Bernoulli's principle is stating there is there's less pressure on top compared to the bottom because the fluid is faster moving over the top than the bottom, and this allows for lift in the upwards direction. Now, however, this is only one component of lift. Okay, there's kind of a common scientific misconception why that this Bernoulli's principle, while it is a factor that affects lift, it is not the main cause of lift force. Okay, and this misconception is compounded by an explanation called the path length or equal transit theory that is very incorrect and unfortunately is taught in different textbooks there. Okay, so here's the issue with the path length theory. Okay, and this eye diagram up top here, okay, exhibits this. Okay, the path length theory states that two molecules starting together at the front of the foil. Okay, so one of these molecules will go over the top and one will go around the bottom. Okay, this path length theory incorrectly assumes that the molecule at the top they'll meet up at the back of the foil. The molecule at the top will have traveled farther due to the shape of the attack of the object, okay, compared to the molecule at the bottom there, okay. What's important to note there, though, is that the molecule at the top there is going to travel much faster, okay, and it actually beats the molecule coming from the bottom there, okay, to the back of the foil or the particular object. Okay. Also, okay, this attributes to the pressure differences between the top and the bottom of the foil, okay, but it ignores the fluid turning force. Okay, the fluid turning force is going to be the largest factor. Okay, the turning of the fluid force is going to be the largest factor there in determining lift force. So again, make a star somewhere on this, or star somewhere in your notes here. But the primary factor in lift force is going to be the turning of the fluid flow by a solid object. So let me repeat that there. The primary factor in lift force is the turning of the fluid flow by a solid object. Okay? The fluid is with the turning of the fluid flow. What this is that the fluid is turned in one direction and lift is generated in the opposite direction, which is Newton's third law there. Okay, and this is affected by the angle of the attack of the particular object there in the fluid. Okay, so for lift force there, okay, lift is a mechanical force, so a solid object must be in contact with a fluid, okay, in order for lift force to occur. If we don't have a fluid, no lift force can occur. So this is why in space here, okay, because there's no fluid in space, okay, no lift forces actually occur in space. Lift can be generated by the difference in velocity between the solid object and the fluid. Okay. Therefore, not only do we need a fluid for lift force to occur, but we need some sort of motion or movement or some velocity happening. If there's no motion in the particular object, okay, no velocity, there won't be any lift force occurring. All right, so let's take a look at the turning of the fluid flow by a solid object. Okay, so let's say we have a symmetrical streamlined airfoil. Okay, it's traveling from right to left. Okay, if we were to add a small bump to the leading edge, okay, what this does there now is, okay, we would draw if we would draw a line from the back, okay, towards the new leading edge there, okay, of the particular object moving through the fluid, okay. This in turn there, okay, will create a new leveling point for this particular object, allowing it to be more curved on top. So let's apply, we also need to understand with objects and fluids there, we need to understand the Magnus effect, okay. And the Magnus effect essentially is using Bernoulli's principle, where faster moving fluids, okay, have less pressure, slower moving fluids have greater pressure, but we apply it to spinning balls, okay? Spinning balls generate lift forces, okay, causing the Magnus effect, okay? The lift force caused by a spin is called a Magnus force, okay? Now, if we look at this ball here, okay, this ball here is traveling from left to right, okay? So it's going to the right. This particular ball has what we consider top spin. So it's going to the right and it's spinning down, okay, or spinning from the top down into the particular direction to the right. Okay? So what you'll notice here, okay, as this ball spins down there, okay, towards the right, okay, the air molecules hit the ball going the opposite direction of which the ball is spinning, okay? So this creates a greater pressure at the top. Okay? Now at the bottom, you'll notice that the ball is spinning, okay, towards the left, if we're looking at the bottom. The fluid is flowing to the left, okay? Therefore, the air molecules are moving faster from at the bottom of the ball, creating less pressure at the bottom. So more pressure on top, less pressure on the bottom. This causes a lift force to move down, okay? Not only with Bernoulli's principle there, okay, but we talked about the fluid turning force, okay? So the fluid turning force states is that faster flowing air, okay, which happens at the bottom or at the top there, will end up causing this ball to drop towards the ground or go towards the area of the fluid that is less dense, okay, or is faster moving. So in case of a top spin, if you see top spin on a ball, this will cause the ball to hit the ground sooner compared to a ball that does not have top spin. Now, we can also have more things other than top spin because the Magnus effect can occur in any direction. Top spin, again, causes a ball to dive, landing sooner than another ball. Okay? Oftentimes, this is used in tennis there to allow you to hit the ball faster while keeping the ball in the court. Backspin, okay, is the opposite of top spin. This keeps the ball in the air longer. And golf clubs, okay, oftentimes will be angled up there to allow for backspin to be implemented on the ball, allowing the ball to travel further in the air. We also have side spins. These cause movement to the right or the left. This allows a soccer player to kick a ball, causing it to turn or to curve left or right, okay, making it more difficult to stop when shooting on a goal. It also can happen there as a pitcher there is throwing a curveball, allowing that ball to move left and right. Now, the effects of dynamic fluid forces, okay, we know the equation for force, okay, force equals mass times acceleration. So if we would restructure that equation, okay, solving for acceleration is going to be force divided by mass, okay? And we've seen this equation before, okay? Therefore, okay, if we would plug in this equation in for force up here, okay, we could create this equation down here for acceleration, okay? And what this causes here with our dynamic fluid forces, okay, if two objects have the same size and shape, okay, they will experience the same dynamic fluid force there, okay? But the more massive object will experience less acceleration, okay? Meaning that a more massive, or in general terms, a heavier object there, okay, it'll be more difficult to get that particular object spinning in the air, okay, compared to a lighter object, okay? Now, if both objects are spinning in the air at the same speed, okay, the lighter object there will end up slowing down its spin, okay, a lot quicker compared to that heavier moving object, okay, if they both started spinning at the same speed in the air, okay? Now, why this is important there, okay, it's why less massive objects will curve more easily, okay? Meaning that I can get a ping pong ball, okay, to change directions a lot faster compared to a baseball. A baseball weighs more, it's more massive, so it's harder to accelerate, okay? That baseball, it's harder to spin that ball faster compared to spinning that table tennis ball, okay? And this is partially one of the reasons why different size and shape balls will travel different distances through the air. So here's an example of this, okay? Due to the Magnus effect there, okay? If I would hit a Nerf ball, okay, that Nerf ball is going to land a lot sooner than a tennis ball, which will land a lot sooner than a baseball. And that's due to a baseball being a lot more massive than a tennis ball, and a tennis ball being a lot more massive than a Nerf ball. So as you can see, the Magnus effect on the Nerf ball causes it to land a lot sooner compared to the tennis ball or the baseball. That's all I got. If you have any questions, let me know. Have a good day. Booyah!